What's up, everyone? Hope you all had a fantastic weekend. This is Mr. Chun, and I will be going over lesson 5.2.2. As usual, with these videos, I'm not going to go over every single question, but I do want to go over the important ones here in terms of what will help for our lesson today. And so, for lesson 5.2.2, this is Pythagorean triples. So, I mentioned at the end of class for first and seventh period that for this lesson in particular, it's going to be an application of Pythagorean theorem. Now, let's say by the end of this lesson, you just want to use Pythagorean theorem and you don't care about new shortcuts. Well, that's completely fine. But I hope you will realize that after going through a few examples of these, this is basically just going to tell you a shortcut on what certain side lengths may be just based off of what is given to you. And so with 5-59, I just want you to work through this and practice some sine, cosine, and tangent. If you're not familiar, on Friday we learned about special right triangles, which I'll provide that separate lesson for, that video for. And so looking at whether 30, 60, 90 triangles or whether they are 45, 45, 90. So I'll do a quick review of one of each of those examples just to help you out here. But then eventually our focus today is going to be on Pythagorean theorem and understanding what it means for it to be a Pythagorean triple. So to start, we're looking at part A, and so we see this 60-degree angle. If we have that 90, then this is going to be 30 degrees. So we have a 30, 60, 90 triangle. So I'm going to go ahead and make our little tic-tac-toe board. With a 30, 60, 90, you just write 30, 60, 90 on top. And then it's going to be x, x root 3, and 2x. Now, this 12 here is across the right angle, so that means 12 is the hypotenuse. That's going to go here. Now, if 2x is equal to 12, then half of that is going to be the short leg, which is 6. And so the 30-degree angle is going to be across the side 6. And then lastly, the 60 degrees is going to be across the x root 3. That's the longer leg. And so if you notice, because x is 6, we're going to put this 6 in here, and then you're just going to slap on a root 3. And that's our answer for part A. Those are the two missing side lengths there. Okay, going on to part B. This time we have a 3, but we notice there's a little tick mark here and a tick mark here. This means that it's an isosceles right triangle. And the angle measures for an isosceles right triangle outside of the right angle is that both of these are going to be 45 degrees. So this is another example of a 45, 45, 90 triangle. So same thing with the tic-tac-toe board. We go ahead and we put 45, 45, 90. We get x, x, and x root 2 because the two legs of an isosceles right triangle are the same as shown through these little tick marks here. And so since we know that one of the sides is 3, that means the other side has to be 3. And then for the hypotenuse, that's going to be a 3 with a root 2 on it. And so that'll be nice and easy there. And so those are the missing side lengths for part B. Now, part C, we have no angles, and with this time we have two sides. And we're not looking for an angle here. We're not doing inverse trig. We're using Pythagorean theorem. We need to use Pythagorean theorem because there are no angles, and we're trying to find a missing side. And so that's going to be the third side. And remember, with Pythagorean theorem, it's a squared plus b squared equals c squared. And so in this case, the hypotenuse here is c squared. And so we're going to go ahead and plug things in. 3 squared plus 4 squared equals c squared. And so when we calculate this out, we have 9 plus 16 equals c squared. 9 plus 16 is 25. And then we take the square root of that. So c is equal to 5. And that's the hypotenuse there. So that's essentially how we go through Pythagorean theorem. I know for some of us it's been a while. I know recently, and it might have been on homework. But we're going to be seeing some Pythagorean theorem examples today. But I do want us to keep in mind, I actually want to show part F and part I here because there's going to be something unique about this. With our part F here, we have a side length of 5 and a side length of 12. And then the hypotenuse is across the right angle, so that's our C value. So I'll put the work to the left here. We have 5 squared plus 12 squared equals c squared. 5 squared is 25. 12 squared is 144 equals c squared. So adding these two together, we get 169. And then to solve it, we take the square root of both sides, and c ends up being a nice number, 13. So then with I, you might notice already that we have a 5 and a 13 here, and there's a 5 and a 13 here. So some of you might think, well, maybe that's 12 for the height. So let's check. If we have 5 squared plus, well, I don't have this one, we'll call that b squared, equals 13 squared. 5 squared is 25, plus b squared equals 169. And then to get b squared by itself, we subtract 25 from both sides. B squared equals 144. And well, what do you know? If we take the square root of that, we get b is equal to 12. And that's exactly what we need here. And so why does f and I work out in that way? Well, for starters, they both have that common side length of 5, and it's a right triangle. When we solved part f out, we were already given that this side length was 12, and we had to solve that this for the hypotenuse to be 13. This time for part I, the triangle is upright. They still give us the same side length, but now the hypotenuse is actually the same as what we solved for. So whenever you see those two numbers, it's going to work, and the third number is always going to be consistent. So this is essentially the basis of Pythagorean triples. The same thing works for over here as well. We have a 3 and a 4, and then it makes a 5 when we plugged it into Pythagorean theorem. Now, if I go over here to 8 and 6 for part D, I'm going to make a connection between C and D right now. So with C and D, so D here, the right angle is across the hypotenuse. That means that's our C value. 6 squared plus 8 squared equals C squared. So 36 plus 64 equals C squared. When you add 36 and 64, we get a nice round number of 100. And when we take the square root of that, we get 10. Now, you might not notice it right now at first glance, and you might wonder, well, Mr. Sean, what's the pattern between the two? It's just doing two different questions, but let's think. 6, 8, and 10, 3, 4, and 5. How are these triangles similar? Well, if we take a look at the smallest side here, that's 3. The smallest side for the part D is 6. How is 6 related to 3? Well, it's twice as big as 3. Well, if we look at 4 on part C, then notice it's 8 here, and that's twice as big here. So again, we would speculate if the hypotenuse is 5, then the hypotenuse here would be 10, because everything gets dilated by a factor of 2. So if I were to write the side lengths down in order from least to greatest, it would be 6, 8, and 10 here. Over for part C, it would be 3, 4, and 5 there. So if I were to divide everything here by 2 in part D, I would just get 3, 4, and 5. That matches exactly what we have with part C. So this is where this idea of Pythagorean triples might come up. And that's where part A, if you guys saw it on the bottom here, that's where it sort of correlates. So I'm going to go ahead and erase this. If you need to check back, you can always look back at the video and rewind it. So I'm going to erase this. I'm going to scroll down. And so now we have groups of numbers like 3, 4, and 5, 5, 12, and 13 are what we call Pythagorean triples. Now, why do you think they're called Pythagorean triples? Well, if we put the two words together and separate them, Pythagorean comes from Pythagorean theorem. So a squared plus b squared equals c squared. But then triples. Why are they triples? Well, these are 3 numbers that will always work in any single right triangle. In any single situation, it will always work. So no matter what, whenever you see a triangle with, like, for example, side lengths 3 and 5, the third side, without even calculating using Pythagorean theorem, is going to be 4. It will always work like that. If you see 12 and you see 13 as the hypotenuse, well, then that means no matter what, you don't have to do any work. That missing side length is going to be 5. And so that's why we had this nice little shortcut that we can use, and we can save a lot of time when we're doing our calculations. And so, well, what other sets of numbers are also Pythagorean triples? How many different sets can you find? There's actually a lot. And if you want to take notes on this, there's actually a good amount of Pythagorean triples that will come up, not only in this class, but just in general with geometry. And so if we take a look at our screen, so we know 3, 4, and 5 will work. And then 5, 12, and 13 work. And actually, you know what? I'm going to make this into text so that it's a little more clear. So we have, let's see. So we got 3, 4, 5. We have 5, 12, 13. Here's another one. We have 7, 24, 25. We have another one, 8, 15, 17. Those are the most 4 common Pythagorean triples that you will see. Now, there are 2 more that I'm going to introduce just because I want to give them to you. The other ones that you might see, and these are less common, are 9, 40, and 41, and then 11, 60, and 61. Those are the most common Pythagorean triples. And again, some of you guys might be thinking, well, what about 6, 8, and 10, Mr. Chun? Well, 6, 8, and 10 is just a multiple of 3, 4, and 5. So in some situations, I don't need to write that as an actual triple. Now, if you remember 6, 8, and 10, great. But that always can divide back down to its original Pythagorean triple, which is 3, 4, and 5. Okay. So now that you know this, we can practice it and you can hopefully see different situations. So, for example, if I look at part B here, we have 18 and 24. That's not on the list, but if we think back to what some of these original triples were, what if we divide these numbers? So if we think about like what is the greatest common divisor between these two numbers, 18 and 24, it actually ends up being 6. And so if we divide 18 divided by 6, that's going to be 3. If we divide 24 divided by 6, well, that's going to be 4. So you might probably already have seen that. If that's 3, then this is 4, then this has to have some relationship with 5 based off of our first Pythagorean triple. Well, if that's the case, if everything is divided by 6 and I just have 5 as my third side, well, if you do 5 times 6, you're going to get 30. So that's the way that you use Pythagorean theorem and Pythagorean triples in particular. I don't have to spend so much time setting up a squared plus b squared equals c squared. If I know what it is, then just use it. Right? And so that's the nice convenient thing about Pythagorean triples. So if I'm looking at part E, this one's pretty easy because it's already given for me, right? I have a height of 5 and a hypotenuse of 13. So where do I see that in here? That's my triple. I have 5, 12, and 13. So without even doing a squared plus b squared equals c squared, I have 12 because I know that that's going to work. So then everything else, right? Everything else, if you don't see those numbers right away, or you can't divide anything, it doesn't make one of those triples, you're going to have to use Pythagorean theorem, which is like, oh, whatever. That's normal. That's what I'm supposed to do anyway. So I'm just letting you guys know that's what's going to happen. You're going to encounter numbers that won't fit in with those triples, and that's completely fine. You're just going to have to do the work on your own. Since we are here, I might as well show the example of F here because this situation did come up in class in 5.2.1, and I want to give at least another opportunity for us to practice this. And so if I have the tic-tac-toe board here, I'm going to change colors just because why not? So if I have this setup, and if this is an isosceles right triangle, then once again, this is a 45, 45, 90. So x root 2 as the hypotenuse, but this time the hypotenuse has 6, which is again a little uncharacteristic, but you can still solve it. So I need to set x root 2 equal to 6. So to get x by itself, because they're being multiplied together, I need to divide root 2 from both sides. But I did go over in class saying that you cannot have a square root in the denominator. It's an irrational number. So in order to solve this, you're going to have to rationalize it by multiplying the top and the bottom by the same number. And this one you multiply across, you do not cross multiply here. So on the top, it would just be 6 root 2. But then on the bottom, I gave the shortcut in class. Whenever you multiply the same number by itself and they're both in a square root, the answer is just that number. Because square root of 2 times square root of 2 is square root of 4, but square root of the 4 is going to be 2. So that saves you a lot of time there as well. So that's going to be 2. And technically, we're not done reducing yet because we can simplify this fraction. We can divide the 6 and the 2 because 2 goes into 6, 3 times. So when we simplify, the side length x is just 3 root 2. And that goes in for here and here. Now, how do we know that that works for sure? Well, to check our answers, if I know that that's x and I want to figure out what the hypotenuse is, well, just multiply 3 root 2 times root 2. And if I go back to that same rule that I just showed earlier, root 2 times root 2 is equal to 2, then we have 3 times 2, which is 6. And so that works. So again, whenever that situation comes up, class, remember, set it up the correct way still. The setup is the most important part. And then from there, if you need to divide by a square root, remember that you have to rationalize it out by multiplying the top and the bottom by that square root. Okay. So I'll erase this again. If you need to go back to it, you can go back to the video. So then just to check here. Okay. Nothing too much going on here. With 5-63, there's a lot of questions that you might see like this, where I give you a shape and it's like, okay, we'll find the area and perimeter. So we just got to be careful here. And so here's the nice thing about what's going on here. So I'm just going to look at part C as an example. So this is a trapezoid, yes. So we do have ways to find the area of a trapezoid. However, we don't have this full length here. So let's split it up into a shape that we do know. If I draw that line right there, it makes a right triangle. That means that this is going to be 3, and it's going to have a rectangle aspect here, so that this whole length is 8. Now, you might notice we have a 5 as the hypotenuse and the 3 here. So what does that mean? This is a Pythagorean triple. So without even doing Pythagorean theorem to solve for the missing side, if you remember the triple, it's 3, 4, 5. So that means this length right here, the one that I'm trying to highlight in, is 4, which means that the total bottom is 12. So the total bottom length is 12. So now I have enough information to solve for area and perimeter. Perimeter, pretty easy. We just add the outside. So perimeter would just be 12 plus 5 plus 8 plus 3. That's going to get us about 28. For area, you could either find the area of the triangle and the rectangle, add them together, or just to practice for us, we're going to do the area of the trapezoid. So base 1 plus base 2 is 12 plus, we got to do that more clearly. So area of trap is equal to 12 plus 8 times the height, which is 3. Divide that out by 2. 12 plus 8 is 20 times 3 divided by 2. So 60 divided by 2 is going to be 30 feet squared. So I hope this helps. If you ever have any questions about the lesson, just let me know, and I'll get back to you as soon as I can. Hope you guys have a great rest of your day and a great rest of your break. Bye-bye.